we start the study of the course Mechanics of Materials. This subject is also known as Strength of Materials or Mechanics of Deformable Solids. This course continues from the previous course Engineering Mechanics Statics. Therefore, you are expected to have solid foundation in statics. I strongly encourage you to review statics before starting this course. In this course, we will still be dealing with objects that are in static equilibrium. Therefore, the most important set of equations that we learned from statics still apply here. And that is the static equilibrium condition, that the resultant force vector acting on the body is 0, and the resultant moment vector that includes the moments caused by forces and the couple moments summarized about any arbitrary point also equals to 0. For a 2D problem, these two vector equations can be rewritten into 3 independent scalar equations. Normally these 3, but it doesn't have to be. For a 3D problem, the vector equations become 6 scalar equations. Since we're applying the same principles, what is the difference between this course and the statics course? If you recall, one of the most important assumptions we made in statics is that the object can always be considered as a rigid body that will not deform. But of course, that cannot be true, because if that is the case, then we can literally make buildings and bridges with paper-thin materials that are still able to sustain as much loadings as we want, since they will never deform and therefore never fail under heavy loads. But real materials do deform, and different types of materials have different mechanical properties and therefore different applications. And that is what this course studies. We want to know how materials behave under loadings, so that we can use this knowledge to design structures that are both economic and strong enough to meet the requirements. Before we officially start, I want to first ask you to imagine several scenarios and consider several questions. Scenario 1. Imagine there is a solid shaft made of a certain material, and a machine starts to apply axial forces on it, and the force is gradually increasing. When the force reaches, say, just 10 kN, the shaft fails. It looks like this 10 kN is a very critical value, since it marks the point of failure for these materials. Now imagine another shaft made of the same materials, same length, same density, but it's significantly thicker. And the same machine applies the same 10 kN axial loading to this shaft. The question is, as you may have already guessed, will the second shaft also fail under this same critical loading? Your answer is probably no. The second shaft is a lot thicker, in other words, has a larger cross-sectional area, therefore we expect it to be a lot stronger and it should be able to sustain a larger load. This tells us that it seems that the actual magnitude of the loading is not critical to determine how the material behaves. That seems to be determined by force over area, and this is known as a stress. Scenario 2. I am holding the same chopstick, but in image 1 I am twisting it, and in image 2 I am bending it. Let's assume I am applying exactly the same couple moments on the chopstick, but in different directions. The question is, will the chopstick behave the same in these two situations? The answer again is no. From your own experience, you can probably tell that from twisting the chopstick is going to split open, a failure from shear stress, while from bending the chopstick will break open, a failure from normal stress. This tells us that even if we apply the same loading on the same member, depending on where and or how we apply it, the material will behave differently. Scenario 3. Imagine the same situation that I'm bending this chopstick, and again, as illustrated here, my fingers apply the couple moments on the two edges of the chopstick. The question is, will the chopstick fail at where the loadings are applied? In other words, will the chopstick fail at the edges? Again, from our experience, we know that the chopstick is most likely going to bulge up in the middle like this. and eventually breaks in the middle. This tells us that the deformation, even failure of a member, is not directly related to the external loadings, but is determined by the internal reactions developed in the member. Hopefully, through these simple scenarios and questions, you start to bear in mind that it is the internal reactions responding to the external loadings that causes the stress distribution in the material, shear stress or normal stress, and that leads to material deformation and even failure. This understanding is crucially important in the study of this course. Now I would like to give you a general overview of this course. It might seem to you that in this course we are going to cover a lot of information, so I hope this overview can serve as an outline so it will be clear to you in terms of what skills you are expected to obtain and what kind of problem you are expected to solve after you complete this course. Normally, we will start with a structure with given loading information. Then we need to determine all the external loadings, which normally means that we need to solve for the unknown support reactions. The support reactions are also external, if you recall. And then we need to determine the internal reactions in the member. Sometimes you only need to apply the method of sections once or twice if a specific location is given. But you might also need to make the internal reaction diagrams like shown in these two images to determine where the maximum internal reactions occur. By the way, you should have learned all these in the course of statics, so if your skills are rusty, you should review statics. From statics, we also learned that there are 4 types of internal reactions. Like shown in this image, along the axial y-axis, we have a normal force N and a torsional moment T. And along each of the x and z axes, we have a shear force V and a bending moment M. So overall, there are 6 components. As you will learn in this course, these different internal reactions cause different stress distributions in the member, and usually the stresses are combined. In the simplified analysis that we will learn in this course, normal force and bending moment both cause normal stress sigma, and torsional moment and shear force both cause shear stress tau. These equations consist the heart of this course. I want you to pay attention to these equations and notice that how the numerators of all these 4 equations are the respective driving forces, and the denominators are all combinations of geometric parameters such as area, moment of inertia, thickness, etc. And talking about geometric parameters, it is often necessary to do geometric analysis of the cross-sectional area of this member. After that, you will learn how to determine the state of stress of a particle in a specified location in the member. Let's use a cube in an established coordinate system to represent this particle. Again, this cube only represents a single particle, in other words, a single point in this member. The cube has 6 independent surfaces, top, bottom, front, back, left, and right, and normal stress sigma is always normal or perpendicular to the surface. So there are overall 6 normal stress components along the positive and negative x direction, positive and negative y direction, and positive and negative z direction. And on each surface, there are 2 shear stresses, tau, that are both tangent to the surface. And this is known as the general state of stress. But if there is no stress distribution along the z direction, then the particle can be simply represented by a square in the xy plane. There are only a pair of normal stress equal and opposite along the x direction normal to the side, and another pair along the y direction, and shear stress with the same magnitude that is tangent to the side. And this is known as the planar state of stress. And for the same particle at this exact same location, if we change its orientation, the state of stress will change accordingly and the new stresses can be calculated. And this is known as a stress transformation. Then we will learn how to quantify the deformation of the materials. It could be a simple size change, or shape change, or a more complicated deformation characterized by an elastic curve. And lastly, with what you will learn in this course, you should be able to design simple mechanical structures that are both economic and sufficiently strong. And that is the general overview of this course, Mechanics of Materials. Remember though, the actual stress distribution in real material is very complicated and a detailed analysis is beyond this course. If interested, you are encouraged to study the more advanced courses such as theory of elasticity or theory of plasticity. So in this course, we will make many assumptions and use much simpler mathematical models, and the goal is to teach the basic skills in the subject. Let's look at the cross-section of a solid shaft. By the way, in this course, we limit our discussion to continuous, cohesive materials only. This means that the material properties are uniformly distributed within the member, and there is no void, disconnection, or breakage in the material. From the statics course, we learned that there can be a maximum of 6 independent internal reaction components, 3 internal forces, and 3 couple moments. I'd like to remind you once again that if you are not sure how to determine the internal reactions, you need to review statics. We also learned from statics that these 6 are in fact the resultant forces and resultant couple moments summarized about the x, y, and z axes respectively. The actual internal forces are distributed throughout this cross-section. We will learn more about how the internal forces are distributed later in this course. Normally, these resultant internal reactions are placed at a special point, the centroid point of the cross-sectional area. Let's look at a very small area, a differential area, delta A, on this cross-section. And the force acting on this small area is delta F. Let's zoom in on this area. This force delta F can be resolved into 3 components along the x, y, and z directions respectively. Again, the first component along the y direction is the normal force, and the x, z components are shear forces. When this area delta A approaches 0, the area becomes a point, and the normal stress sigma at this point is defined as delta Fy over delta A. And the shear stresses tau at this point are defined as the force components along the x and z directions over delta A, respectively. Note that the shear stress has 2 subscripts. The first subscript indicates what surface it is. Surfaces are defined by its normal direction, in this case, the y direction. Then, the second subscript indicates the actual direction of the shear stress vector. Since stress is defined as a force over area, in the SI unit system, its unit is Newton over meter squared or Pascal, and in the US customary unit system, its unit is pound over inch squared or PSI. Therefore, for an infinitesimal area delta A on this cross-sectional surface, it could have a maximum of 3 independent stress vectors acting on it, a normal stress sigma and 2 shear stresses tau, corresponding to the 3 internal forces. But does a particle only have one surface? Normally, a particle is represented by a cube with infinitesimal sides. We all know that a cube has 6 surfaces: top, bottom, front, back, left, and right. Therefore, on each surface there is a normal stress sigma that is perpendicular or normal to it, and also 2 shear stresses tau that are tangential to it. We call this the general state of stress of a particle. If you recall what I mentioned in the introductory video for this course, in mechanics of materials, we still only study objects that are in equilibrium. Therefore, the equilibrium conditions still apply. Derived from the equilibrium conditions, we can have the following two conclusions. First, the normal stresses along the same direction must be pairs with equal magnitudes and opposite directions. Secondly, the shear stresses within the same plane, in this case the YZ plane, must have the same magnitude. Also, their directions must follow this rule, that the two adjacent shear stresses must be either towards each other or away from each other. And this is called the complementary property of shear. Therefore, the general state of stress of a particle can be characterized by 6 independent stress components. There are 3 normal stress components along the x, y, and z axes respectively, sigma x, sigma y, and sigma z, and 3 shear stress components within the xy plane, xz plane, and yz plane respectively. When we reduce our 3D analysis to 2D analysis, in other words, we focus on the state of stress within only one plane, in this case the xy plane, then there are only 3 stress components: the 2 normal stresses along the xy axis and the shear stress within the xy plane. And this is called the planar state of stress. Stress is a variable. Here, let's look at the normal stress. It changes with location across the cross-sectional area. The integration of the normal stress over this area equals to the normal force. Stresses are tensor quantities. Therefore, the actual normal stress distribution is complicated and also beyond the scope of this course. Instead, an approximation using the average normal stress is generally sufficient. The average normal stress is simply defined as the total normal force over the total cross-sectional area. This corresponds to an idealized uniform distribution of the normal stress over this cross-section. This means that we assume the normal stress is the same everywhere on this cross-section. Similarly, the shear stress in the x direction also varies with location, and its integration over the cross-sectional area equals to the shear force Vx. And again, for convenience, we define the average shear stress as simply Vx divided by the total area, and that also indicates an idealized uniform distribution of shear stress. And same thing for the shear stress in the z direction. The average shear stress in the z direction is defined as shear force Vz divided by the total area. Now please answer the following questions.